Have you ever just, looked around and noticed that a certain curve seems to pop up everywhere? I'm talking about the arc of a thrown ball, or maybe the big sweeping curve of a bridge. Well, that shape has a name, and it's all built from a really powerful mathematical blueprint. So, let's dive in and decode the parabola.
Okay, this sounds like the beginning of a bad joke, right? You've got this massive piece of architecture, some high-tech gear, and a classic move from the basketball court. They seem like they're from totally different worlds, but they are all connected by the exact same principle of design and physics.
And no, the answer isn't some kind of trick. It's a shape that is so perfectly suited for its job that both nature and engineers landed on it over and over again. And that shape is the parabola.
And when I say it's everywhere, I'm not kidding. It's literally all around us, just hiding in plain sight. So let's start spotting some of these parabolas out in the wild.
So what exactly is a parabola? Well, officially, it's a perfectly symmetric, U-shaped curve. And that symmetry is everything. It's known for two incredible properties. First, it is the exact path any object takes when it's flying through the air, thanks to gravity. And second, it has this wild ability to grab waves, like light or sound, and focus them all down to one single super powerful point.
And this is what brings us back to all those examples. That beautiful arc of water in a fountain? Yep, that's a parabola. The little reflector dish inside your car's headlight that makes a strong beam? That's parabolic. Suspension bridges get their strength from this shape, and satellite dishes use it to focus a faint signal. It's a real workhorse of geometry.
But where does a shape this perfect even come from? It's not magic, it's all math. Every single parabola you see can be drawn using a specific kind of equation that works like its blueprint. Let's take a look at the three main blueprints we use.
Welcome to the engine room. The quadratic function. See, any equation that has an x squared as its highest power is a quadratic. And when you graph one, it will always be a parabola. No exceptions. Those letters A, B, and C, think of them as the secret codes that control exactly how the parabola looks and where it sits on the graph.
Now, the cool thing is we can write this blueprint in three different ways. You can think of them as different tools for different jobs. Standard form is kind of the default, and it instantly tells you where the curve hits the y-axis. But vertex form, that's the one you want if you need to find the highest point of a rocket's flight, because it points you right to that peak. And factored form? Well, that's perfect for a bridge engineer who needs to know exactly where the supports hit the ground, because it shows you the x-intercepts. It's the same parabola, just seen through the lens that's most helpful right now.
Okay, so let's use those lenses and start decoding the key clues that define every single parabola, starting with the most important piece of the puzzle.
The vertex. This right here is the heart of the parabola. It's that one spot where the curve stops going in one direction and completely turns around. If the U-shape opens up like a bowl, the vertex is the absolute bottom. If it opens down like a hill, the vertex is the very peak.
And you can see it right here. The curve is climbing, it hits that absolute maximum point, that's the vertex, and then it starts its perfectly symmetrical journey back down. Everything is built around this one critical point.
And running right through that vertex is something called the axis of symmetry. It's this invisible vertical line that just slices the parabola into two halves that are perfect mirror images of each other. If you find the x value of the vertex, you've found this line.
And finally, you've got the intercepts. The y-intercept is pretty straightforward. It's just the one place the curve crosses the vertical y-axis. But the x-intercepts, which are often called the roots of the equation, are a bit more interesting. A parabola might cross the horizontal x-axis twice, or it might just touch it once, right at the vertex, or it might miss it completely. So we've got all these clues, right? The vertex, the axis of symmetry, the intercepts. How do we actually put all these pieces together? Let's walk through how this builds into a foolproof way to draw the perfect curve every time.
Here it is, a reliable 5-step recipe. First up, just glance at the A value. If it's positive, the parabola opens up. If it's negative, it opens down. Easy. Second, you can find that line of symmetry with one simple formula. X equals negative b over 2a. Third, since that formula just gave you the x value of the vertex, just plug that number into your equation to find the y value. Step 4, find your intercepts. And last, just plot those key points you found and connect them with that classic smooth U-shape.
And there you have it. This is what it looks like when it all comes together. You can clearly see the vertex sitting at the bottom, that vertical axis of symmetry cutting it right in half, and the points where it crosses both axes. All of that information was hiding in that one little equation.
Now, like with any good blueprint, there are a few common little traps you can fall into. But don't you worry, we're going to call them out right now so you can sidestep them like a pro.
Okay, the number one culprit, always, is tiny little sign mistakes. That negative sign in the vertex formula? So easy to forget. Another classic slip-up is just accidentally drawing the parabola opening the wrong way. Keep an eye out for these and you'll dodge the most common headaches.
So, picture this. You get a homework problem that says y equals 4x squared minus 6. Looks simple enough. But then you go to use that formula, x equals negative b over 2a, and you hit a wall. Wait a second. Where's the b term? There's no plain x term in there at all. And hey, if you're scratching your head at that, you are not alone. A parent on Reddit who was helping with this exact type of problem posted, "Man, what a sneaky question for her first time with this." It's a classic math curveball.
But here's the secret. The blueprint is always ax squared plus bx plus c. If you don't see one of those terms, its number is just 0. So in our case, b equals 0. And the formula still works perfectly. X equals negative 0 over 2 times 4, which is just 0. The trap is meant to make you panic and think the rules changed. They didn't.
So let's bring this all back to the real world. Whether you're looking at the flight path of a baseball or a massive, beautiful bridge, you now know that the exact same mathematical blueprint, the same rules, the same clues, is running the show underneath it all.
So why does this one shape matter so much? What's the payoff? Well, its physical properties are just incredibly useful. That focusing power allows us to concentrate energy, whether it's weak radio waves for a satellite dish or sunlight for a solar cooker. Its natural arch shape distributes weight perfectly, letting architects build these incredibly strong and elegant bridges. And because its path is so predictable, we can calculate the trajectory of just about anything. It's really a cornerstone of physics and engineering.
So, we've decoded the blueprint. We've seen how it all connects back to the world we live in. The only real question left is, now that you know what you're looking for, where else are you going to find it?